So I said we're in product development a little bit deeper than we want to be, but it's actually a lot of fun. We're having a ball with it. I would want to mention something to all of you that may be escaping your notice. We make the GevQ box, and we package it with a very nice cable, and we put it in a real nice box, and then we charge you the ship for it. All the files to make this are open source. You can download them and make it yourself. Is Jason Arnold here? You did 2 of them, didn't you? 1 or 2? 2. He did 2 of them. Kelso can put one together in 4.5 hours.
No, it's fine.
And Kelso's a whiz at this. Ed Clausen actually did the first design, and we had talked about it. It was a shield for an Arduino upside down, because it was about 3 times larger than the Arduino. And you turn the Arduino upside down and plugged it in. And it's because I wanted the Amphenol connector. And that's what you use in cars. The Arduino has little flimsy pins and stuff. You can't use that in a car, and it worked. So we were after the connector and maybe seal out some of the stuff. And then Paulo took all this and shrunk it down on one board. I can't even see it. Even getting them produced, we've had a lot of problems. I'm waiting right now. I've got 30 of everything I need except the wireless module, which I had no hope before the 19th of August, because they've gone to a new wireless module. So it's hard to produce, and it's hard to build. But you can build it. You can just download the files and do it. And all the software is open source. We're going to do the same thing with the JLD 505. This one's not hard to build, although we did use a lot of little components. And similarly, our BMS, which we're going to talk about next. But all of this is open source stuff. That is more an assurance than a directive. You don't have to build them, and you don't have to program in C++. If I do a Mark Marietta clutch thud response, where you have a heart attack on the carpet, this lives on. It's all available. The software does. There'll be other people do additional modules for it, and it'll be extended and so forth. It's specifically not proprietary, and that, I think, increases its value dramatically in that everybody knows how it works and can extend it ad infinitum. So Ed did the original hardware design. Paulo reduced the board size and increased the complexity delightfully. And Colin Kidder has done most of the code work. I did the original specification on it. I think it's a game changer. It's going to open the door to all sorts of other components. But we have other products in development here, but they're all open source hardware and software. You can build them yourself. I think it'll cost you about $100 more than what I'm charging for them when you get done. But party like a rock star. And we always welcome help on the software side. It's all done in C++, actually the ID, Arduino Sketch is the name of it. But it's really C++ without the STL library. You don't get to use STL, but other than that, it's very object-oriented and so forth. And so that's going to be kind of the same deal with the JLD 505. We're a little vague on what it does because we haven't got the software yet, really. And you're going to redo software anyway when we do. And so it's kind of open-ended. So these are kind of the dream team, my heroes here. And we're going to let Ed Clausen give a presentation on the big brother of the JLD 505, which we're not calling the 606. Right now it's just the BMS, which is kind of quizzical given Brian Seymour's newfound religion that we don't need one. But I think you'll see that things are a little different. The BMS has been kind of a long time coming on a particular issue. And Ed and I have argued back and forth through 60 schematic diagrams and almost killed each other over this. We remain friends, but it's very strange that we do so after all of that. Your battery, I believe, I have a theory that you can predict the early demise of your cells by comparing their voltage under extreme load. In other words, you have a cell that looks perfectly, Brian's, when a cell goes sideways. I'm not really so much interested in detecting when a cell goes sideways. I can actually do that now. I want to know when one's going to go sideways 2 weeks from now and be able to tell ahead of time. And I believe, and I do not have good test data to back up this claim, it's one of Jack's theories, that if you measured the voltage of an entire series of cells and you measured the voltage of each cell and they all look perfectly good, if you had a cell that was imminent to demise, then it would show up first in the 800 or 1000 amp range, the 8 to 10 C range. And at that point, it would sag further than the other cells. And if you started to see that, even though the cell operated perfectly normally, and at static, it looked perfectly normal, you're still going to lose it. And so it would show up there before it actually caused your car to cease operation. So one of the basic tenets of this BMS is the Lee-Hart bat bridge, which Lee-Hart years ago designed a very simple circuit with a diode that measured 2/2 of the pack. And as long as they were the same, the diode was out. And if one of them got more than 2.5 volts different, the LED lit. And that was his version of a BMS. And not a bad take on one, actually. I've been honored by it ever since then. We're going to have up to 4 pack segments. And you can have any number of cells in any of the segments. You'll be able to configure that. And this is going to compare the voltages of those segments all the time, statically and dynamically and under load. Now the problem is, how do you measure a pack segment and not take more current out of one part of the battery than the other? And Ed keeps sending me all the prior work done with BMSs, and I keep marking it up and sending it back. No, we're not going to do that. And then he goes and finds another one and sends it to me, a variation of about the same thing. And the reason it doesn't matter for those guys is they're going to top balance the cells anyway. We're not going to top balance them. So we have to take the same amount of current out of the top pack segment as the bottom. And a battery looks a little bit like a ladder. It's hard not to reference to the bottom of the pack. And so if you measure the top quarter, you have to carry current through the bottom quarter. And if you measure the next quarter, you again carry current through the bottom quarter. And by the time you go through 4 of them, this one's drawn 4 times more current than this one. And so it's been quite a thing. We've kind of come up with a sample and hold capacitor or an airlock where we connect the segment to a cap and then disconnect it, and then connect it to an ABC and then disconnect that, and then connect the next segment to the cap and charge it and disconnect it and connect the next segment. And it takes a lot of circuitry and some very kind of expensive MOSFET switches that we don't know if they'll work, and some good caps and so forth to be able to do all this. And so we actually wind up with another board just to measure voltage. The heart of it is a chip that was announced a year and a half ago by a company called Sendai. It's designed specifically to measure coulombs for EVs. But it does so at an incredible resolution, and we're just starting to see now through experimenting that maybe we're measuring it too fine a resolution, because we start to see noise from other devices, like he had a inverter on it, but we're going to have that from our inverters or controllers or even DC to DC converters are all going to show up there, or going to wind up back in software averaging the current and not have it. But I still think that the Sun9, we're actually going to use their development board to work out a deal with them to do an external shunt for it, that it's going to be the most accurate coolant counter available for any transportation device. So that's the two basic rubrics. It won't balance anything. It has no power electronics of any kind, but it should very accurately measure voltage without parasitic loads, I hope. And it should very accurately measure current. And that gives us, with a couple of communication interfaces, CAN and so forth, the ability to do a lot of things, control charters and interface with the regular GenQ and so forth. But I'm going to Ed do a little presentation. We have Colin, our software guy, and Paul and Kelso, our hardware guys, and I'm very good at making up stuff. So between the group of us, we ought to be able to answer any questions. Let's let Ed give us a presentation first.
All right, thanks, Jack, for the intro. So, Jack came up with the idea here, and that's why we got him on the list of characters. Probably too, when you look at the specs on this Semnon chip, that's where you get the light kick, because it actually can do that. It's pretty incredible. So I'll be going through that and then show you actually some prototypes I've built and some of the data that I've been getting out of them. So it's basically a review of what I'm going to do. First, just this chip is called SFP100. It's not for sun timing, but it's actually some name they came up with. Just a little bit of description, what it looks like, and block diagram, how they're doing these things. And then what we've been coming to call the EVTV BMS. I'll show you what the design theory behind that was and how that's all put together, and then finally some measurements of it. So just to start out with, we, like Bryce said, got done drinking the Kool-Aid. Well, we're going to still use the same letters, but we're going to have to change the meaning, because that M is going to be for monitoring. It's not going to be for doing any charging or changing cell charge levels. It's just designed to monitor, and then you do something with the data. Now, it may go to display, it may go to GenQ, but it's not going to change any state of charge of the batteries. So this Semnon chip, it's a precision IC chip that can do simultaneously current measurements, coolant counting, temperature, and voltage measurements. And it uses two 24-bit delta sigma analog to digital converters. And that's 2 to the 24th, which is a very small number. They claim an offset error of less than 150 nanovolts. Now, I imagine you can do that in a laboratory when you don't have a lot of shielding around, but probably not in an electric vehicle. But we'll see what comes out. But one thing that it does do for you is it gives you stability, and that came up with the question with Paul's talk, that you can measure thousands of amps and milliamps with the same input. You can measure thousands of volts and millivolts with the same input. So it does give you that incredible range of measurement ability as well as precision. And part of what they do to be able to get that kind of range and precision is that they have this continuous calibration that's occurring. And you have this base calibration that will be calibrating the shunt millivolts, but once they have that, they're doing an algorithm that's looking at noise, it's doing a bunch of filtering, because one of the things, little side note about 24-bit Sigma Delta ADC is not your normal sample hold integrator kind of analog to digital converter. It actually is like a chopper. It splits the signal up, does some digital DSP filtering, and then reintegrates that signal into a digital, gets you a digital word. And that's how they're getting this 24-bit resolution. And as Jack pointed out, they're out of New York City. I don't know. They don't do any fabrication here. It's all done offshore, I'm sure. But this is basically the block diagram of that thing. And it shows that there's two ADCs, and what they do is they use one for doing current measurements. So the shunts out here they have a bunch of low-pass filtering. That's the first thing that goes on. And then the second ABC is used to measure pack voltage as well as thermistors. And they have the ability to measure a number of thermistors on this board, or through this chip. And actually into their prototype board or their development board will point out why they have to have so much thermistor measurement. It's not really guided towards or needed for the pack. They didn't really think about the pack, but it's really about measuring the temperature of that shunt. And basically, that shunt, one of the reasons is that they can get the accuracy is that they know the precise temperature of the shunt. And one thing that goes on with the shunt is that, this is connected to the outside world through some wire. And this essentially is going to be a dissimilar metal contact here, which is basically a thermocouple, which is going to generate an EMF under temperature. And that, when you're dealing with, sub-microvolts, that can affect your measurement. So they're using a lot of measurement of shunt temperature to be able to compensate the measurement and get a high accuracy. So this is what their development board, or their evaluation board, they call it. And you can see what they've done. They basically attached the shunt directly to the PCB, and they have 3 thermistors sitting right on the surface of the shunt. Now, I know that there's thought of this as being an evaluation, but it certainly would never be possible to use this in a car because typically the shunt is sitting out in the engine compartment, and you could not have this level of electronics exposed to the environment of the vehicle. So somehow you have to separate these two, and I don't know that they really thought about that initially, because when I told them, we're going to have a remote shunt, they were a little bit horrified, but I think they finally got over that that's the way this product would have to be used. And this chip would have to reside on some protected electronics, some type of enclosure. They then, part of why the only way you can use this is that this galvanic isolation is very critical. And in fact, in the case of what Paul is doing, what we've done in the JEV-Q, that's really the only way these high precision and very expensive electronics can exist in the cars, to have that isolation that keeps all of the spurious and crazy signals out off of the bus and the board. So the design theory for our BMS was we want to use this high precision Sendyne chip. We want to be able to log the data and isolate that measurement from the batteries. And at the same time, be able to do multiple voltage measurements and multiple temperature measurements, and avoid this ladder effect, as Jeff pointed out, which is one of the problems when you try to measure segments of pack voltages through shunt resistors. And this is just a diagram that shows that. Basically, what happens is that you get this continuous flow of current through the pack, even when the contact switch is open for the whole pack. And yeah, it's only, with these mega ohm resistors for the shunt resistor, it only ends up being a milliamp. Well, it's a milliamp this second, that minute, that hour, so on. And on top of that, you've got 4 milliamps in this circuit, 1 in this set of batteries. So you now imbalance each set of batteries. So the design of the BMS is going to be based on this Sendyne chip. We're using the exact same ARM Cortex processor that we use in JEV-Q, basically to leverage off that design development. Has an EEPROM for data storage, because one of the problems with the Sendyne is, although it has flash inside it for storing calibration constants, it doesn't have any flash for user data. And if you want to do coolant counting and be able to turn your car off and turn it back on and retain that number, you need sometimes storage. So we use the same 256K EEPROM storage. It has CAN bus, it has serial communication, and that goes to, if you want to drive some serial display, here it easily come out. And then there's I2C communication. That's going to be used to communicate to this voltage high voltage multiplexer that we're going to be developing too. And also, this board has the ability to multiplex 4 thermistor signals. And of course, it has the hard power supply. isolation. So this is what the prototype board looks like. It has the Sendyne evaluation unit actually plugged into it instead of being integrated, just like we did the first GEM-Q. This is the easier way to build up the first ones is to stack, and eventually they'll be integrated onto the same PCB. Although the Sendyne has a very special circuit design, requires multi-layers, and actually they have requirements about distances where MOSFETs and resistors are placed with respect to their chip to reduce noise and thermal drips. But uses again a same AMP-Seal 35 connector, same kind of isolation for power, USB connection. And then through the AMP-Seal is a lot different than we have in GEM-Q, obviously, because we have different signals coming out. And it can interface to basically any shunt. You just can program that. I used a 100 milliwatt, 600 amp shunt, but the Sendyne unit, they're basically claiming you can go down to a 10 millivolt shunt, or probably you can go up to 500 millivolt shunt, whoever really got it. So the other piece of this is having a board that does the high voltage multiplexing, and I separated that to the second board mostly because it's high voltage. We really didn't want to have to deal with additional isolation on the main board. Again, this board has the hardened power supplies, has a 14-bit AEC, just the standard AEC, has isolation on all the inputs, and has the ability to measure 4 voltage points. And this is one of the things that I've implemented to avoid this parasitic load. Is to use this bidirectional MOSFET. MOSFETs are great switches. They have a some can have a very, very low turn-on resistance, so that they're basically almost 0 or milliohm resistance. But they do have one problem, is when they're turned off, they can conduct in the reverse direction. So when you take two MOSFETs and you put them back to back like this, now when they're off, they don't conduct in either direction. And when you turn them on, there's basically 0 resistance conducting in both of them. Interfacing that to a type of photo isolation chip that drives those is the way the whole isolation is done on this board. And this is what this chip from EVCON looks like. It's basically has no power supply connections to it, no ground connections. It just uses the power generated by the photodiode LED that's in here, and the photodiode on this side, to generate a signal that can drive the MOSFET.
Wow.
Very elegant way to do galvanic isolation. So this is what the whole circuit looks like for this high voltage MUX. This is all the MOSFETs, a series of MOSFETs. We're basically going to be just selecting 2 that are connected to one segment of the battery pack, and then you shut those off, connect the next 2, shut those off, connect the 2. Those interface into the ADC, which is read by a I2C isolation chip that sends that out to the BMS board. And so this just looks a close-up again of what those bi-junction or bidirectional MOSFETs look like. They're just driven by a digital input that comes from that isolation chip. And then this is what the isolation chip's all set up for, and the I2C isolation. And then just what the ADC is set up. Sampling cap takes about 600 milliseconds for this circuit to charge up, and then the ADC can be ready for the voltage. And on the inputs, basically, let me show you. This is what a deployment of this would look like. This is my battery pack I'm using in my car. And since I have 120 batteries, I would want to divide my pack into 4 equal quarters. So I have that sensor at a voltage sensor every 30 batteries. So there's both going to be temperature and voltage at each of those points. And here's what the board looks like. This is the array of MOSFET drivers, isolation, power supplies, and then same kind of connector, this stitch connector that Oliver showed. This is actually something that Colin came up with about a year ago, pointed out this would be a really great enclosure to use, and we're going to start standardizing on this. Pretty amazing thing that, it's pretty much waterproof. The only thing it really isn't is EMI protected. It's not shielded, although they do have a more expensive version than it is, but I'm not clear that we really need that.
It's filtered, not shielded.
Yeah, filter.
There's some
Ferrite on the input, yeah, but it's really looking at the input signals. They're assuming that you're not going to get any kind of fields that go through it, but
Jack has some copper coil somewhere.
We're going to put it under a copper foil helmet.
so some of the measurements I made just to prove that they can use this particular product with a remote shunt, and that can be calibrated. And they actually never thought about doing that calibration on a remote shunt until they talked to us. So now they've developed some software for that and have built that into the firmware. And then the other measurements I'm showing here is how I discharge the batteries through a grid-tied inverter. So this is their little application that comes with the evaluation board. And this is showing plots of current and voltage on charging from a boosted charger. And as Jeff alluded to, we're now starting to see with this high precision a lot of noise in the current. And a lot of this is due to just the ripple output of the boosted charger. It's something, if you actually go and look at the specs, it does have like a 10% ripple in it in its output. And guess what? That's what we're seeing. It's like a 100 millivolt ripple. Some of this has to do also with even though Sendai has some types of anti-aliasing in their firmware, there is some aliasing going on here because the sample rate is 5 hertz. But as I understand, you can change that to some other value, which we may want to make it less than 5 hertz or more than 5 hertz to move this. And here's a discharge curve. These spikes that you see going up here are due to the grid-tied inverter shutting off periodically to cool down. But this has an even larger amount of noise in it, which is probably related to both some aliasing going on as well as these grid-tied inverters use MOSFETs to channel the current in and out of the inverter, and there's probably some switching going on that besides where it turns completely off and causes some of this noise. In fact, you can see if you look at that plot, there is some aliasing going on. You see this sinusoidal variation in the noise. That's just purely because sampling at some rate that's feeding with the noise that's there. So the next steps for this is we need to write some software for the board. I started doing that, but we sort of need the whole sort of front level, or top level that we have in the JetCube. It's not as sophisticated as the JetCube. It just has to talk to the Sendai board and get the voltage off the MUX board. I have to reorder the MUX board because I ran into this problem that we've done before. Apollo did this, and did this beginning and then again, where these these optical isolator chips, they say they are a certain package size, but it's not standard. It's they call it a wide socket, but it's really not. It's a super wide. It's a huge chip. It's got 8 pins on it, but it doesn't correspond really to any standard for semiconductors. And if you do the layout for the board and you use the standard, then these chips don't fit. So these first MUX boards, I mean. Well, it's just to make the boards over. It's easy enough, but that's part of the reason why I don't have a whole system here this week to put together. Is this board's going to be reordered, and then we have to develop an enclosure for the main board. Again, I think the cinch enclosure would be the way to go, but that would need some machining to adapt that AMSIL 35 to the front. That's it.
And I think it might be worth pointing out that the isolation between the high voltage board and the main board, all that's done over I2C.
Yes.
And so the software is actually going to have to query that ADC and the the other chip, to get the data. So we're doing a lot of sort of passing things by data instead of analog. And I think that will work out pretty well. I don't think the software, aside from the protocol that they give, talk to the Sendine and the ADC, the software is not going to be near the level of effort that a JetQ is. We don't have to have interrupts and heartbeats and so forth, register for various things. But it will be very similar hardware and hopefully price point. But in that way, we should be able to fairly accurately measure voltages and current, and then do some things with that in software and be able to communicate with the rest of the world, the JetQ, OBD2, chargers, that sort of thing, pretty well.
Ed, question.
I'm sorry.
I have a question. The LED, the photodiode that's hooked across the back
Yes,
for the isolation, isn't that in itself drawing some current?
Well, yeah, I mean, the whole system is drawing some current, but that's all up as well.
Yeah, that
It's not in front of the
LED is actually not on the high voltage.
Oh, okay.
That's driving the MOSFETs.
Oh, okay.
That's, we're gonna send data to it and, from the processor, and it's gonna switch on the MOSFETs. It actually never comes in contact with high voltage.
Okay, so basically, like you said before, you're using the capacitor to kind of transfer.
The capacitor is kind of a
voltage.
sample and hold thing, yeah.
Right, okay.
We're going to connect a pack segment to the cap, let it settle, and then disconnect it from the pack and sample it with the ADC.
Are you going to be putting the sensors on the shunt like the Sendine unit had, or?
Well, that's something we may have to deal with. Again, you know, they drive their specs because they have this high resolution chip. And I don't know that it really relates to the real world where you need that kind of precision. What that's going to just mean is that the current measurement will drift with heat. So then your coolant counting will be off, but what's the precision you need? You know,
We
half
had
percent.
initially kind of developed a relationship with them, and Ed has put in quite a bit of effort into furthering that. They have introduced a remarkable chip as a cooling counter specifically for EVs, and so far it appears to have landed with a dull thud, and because it's quite complex, and so they're anxious for somebody to do a what would you call it, a sample application that they can point to.
Right.
That somebody put one in a car somewhere, and so Ed's kind of leveraged that, where they're kind of working with it pretty good. And so, I don't know, and we have two temperature issues. One is the shunt, and then the other one is the pack. We're actually developing some brass bolts that have a one wire for the voltage and two from a CAN-therm NTC thermistor that we'll be using to measure the thing. But as you know, I'm kind of critically aware of spaghetti wiring. And so that'll be a bolt with about 3 inches of wire and a connector, and then you'll have a sheath cable with the 3 wires that will carry that back to the high voltage board. And of course, I don't want to foul our washer, so this will actually be a battery terminal bolt. You'll be getting terminal temperature of the anode about as close as you can get it, even in a laboratory. And so I think that'll be a pretty good feature. But you're not going to be no loops stacked up on top of loops and wires going everywhere and that sort of thing. You get 4 pack segments, 3 wires, and you have to use the bolts that actually go into the battery. And so that'll be kind of a part of it.
Right, we put the bias resistors right there.
obviously, yeah, this is the voltage divider. You have 50K at each sample point on the pack, and then what are you using internally?
2K.
2K. And so, if you got any current through this, it would just burn up the resistor. If you mangled the wires or something, shorted it or something, the resistor would act kind of as a fuse. It's actually right there at the connector, and so it would act as a fuse and simply burn up, and that would be the end of your fire. Brief, short-lived, and not very hot.
But that is one issue about, just to point out, that this design, we can change the resistors, but that pretty much limits you to about 106 volts per segment. In terms of ADC, because ADC only is 2.6 volts. So just the way the voltage dividing works out, that's the limitation. But again, one of the things we want to do is check for now is start data logging what happens when you put the power under load, put batteries under load, and change the voltage. And at that point, you're not going to be at 100 volts on the segment.
See, we could just record off your pack segment voltages anytime you exceed 800 amps. That's
Yeah,
where,
something
we'll
like
just
that.
save that into a special, area.
And again, it's, we can change the voltage divider to accommodate larger packs.
Sure.
I don't think anybody else, myself, has done more, except John, been doing more than, because I've seen it, on 400 volt pack.
And since it's kind of in software, it's really not that important that they be the same size packs.
No, it doesn't.
We can enter the number of cells per segment and do the basic math for you.
What's the,
Yeah, with the microphone,
Yes, that's fine. It's wide.
Ed, you showed the vision of the pack, like 4, is that gonna be the standard?
No, well, it's four segments. You can do it any way you want. We just considered that if the limitation would be what the voltage divider ends up being. So it can't, in this particular implementation, it's 100 volts per pack per segment.
So you could divvy it up further than as long as you don't exceed the.
Right.
But now, wait a minute, you can't divvy it up past 4.
Yeah,
You're limited to 4. The thinking originally was most packs should either be divisible by 3 or 4. But as we've gone along, we don't even need the same number of cells per segment.
No.
We can do that in software, so.
And the reason I ask is my pack's 50, so I'd have to go down to 2.
How about 225s? You know, but you could even have a 30 and a 20, or 2 20s and a 10.
Okay, they don't have to be.
They do not have to be equal size.
Do they have to be even?
Do they have to be what?
Even? Like you get 55, 43?
No.
It's just going to be a software thing.
Yeah, well, it's a little bit more configuration, but then you're going to have to put, the number of cells in each segment, and then we just do the math for you. Richard, back here.
Are you using the agency from the deal board, or have you got another one?
I'm sorry?
For digitizing the,
Which is the Texas Instruments agency. Just standard 14-bit.
so it's your own agency, is that floating?
Yes.
So then why are you bothering with the capacitor?
Well, there is some switching that's going on with those transients and the MOSFETs. That's helps to absorb some of that noise.
So you don't want to fly the agency across?
Well, we try to, this is sort of in development, we're trying to figure out what's the best way to go. Sampling the AEC.
Okay, and are you aware that what we're describing up there is available off the shelf, but bidirectional flying switches?
Yeah, sure.
With the optical isolation?
Well, the video chips off the shelf. There is bidirectional MOSFETs, but to get into the voltage level that we wanted to use here, I did a pretty exhaustive search and didn't find anything.
Oh, I'll show you, okay, come into this one.
Yeah, well.
They release a new chip every week.
Over here, just to beat the 4-link deck again, is that a function of the send line, or theoretically, if you're muxing the voltage anyway, you could have 2 voltage boards and 1 main board at some point? And
Yeah,
all magic.
right, because we're essentially muxing that into a single voltage measurement point at the center.
Okay. So we just have to, for scalability, design it so there may be a second up to N voltage boards in the system.
Yeah, the real limitation there was that it only has the, well, again, I guess, I think about it, you can mux 4 thermistors into, originally we were only thinking 4 thermistors because of their design, but certainly it was more.
Yeah, I think temperature will probably cover. Good, thank you.
All the way in the back, Trace. Richard.
Is it Sendine company that makes the terminal or something?
Yeah.
You self-aware sign of the cyberdyne? Skynet?
So, just so I understood you correctly, the bolt that you're using, brass bolt with a thermistor in it, and so you'll have 2 wires being the lid legs of the thermistor and 1.
We actually drill a small hole in the bolt, put a sense wire in and solder it, center it to the brass bolt. Then we drill a bigger hole on top of a little hole and glue in a little, looks like a bead, it's very small thermistor, and we glue that in at the upper level. But you're actually, that bolt goes down into the anode and should be the closest thing to an internal temperature at the anode that I can think of.
Are there any concerns about picking up noise on the thermistor legs?
Well, yeah, I mean, it's potential, well, again, Sendine has, their front end does a lot of filtering. I think probably what we would do, at least what I've done is some 26 gauge conductor, she was getting once we kind of drill that.
There's gonna be noise everywhere.
Yeah.
I got a question. A lot of this is, not a lot, most of this is going over my head, but once this is on the website and I go and buy it, what am I going to be doing with this? Like, what's it going to show me on a display or something? I don't know what it's doing, actually. I probably missed it or something, but maybe not.
Basic BMS part is to do the cooling counting. It's basically trying to tell you your state of charge of the battery.
Okay.
That's smart. And voltage and temperature is really the diagnostic of the battery degradation.
Okay, so it'd be state of charge and how much do I got left, and okay. All right.
The display part, again, it sort of depends on your car and what you want to see.
Yeah.
Ed actually has got gauges. He's doing analog. A lot of instrument systems already work on CAN, and this device is CAN capable.
The Smart ED has analog gauges, which I like a lot, more than a...
Well, there's such a wide array of cars. You should have what you like, but that's going to be different from what the next
And
guy
this would ultimately send out a signal that a voltmeter would do something with.
We can send
or
out
a fuel
PWMs
gauge.
to an analog meter, or CAN bus commands to a CAN instrument, or CAN bus commands on the CAN bus in the car, which can be picked up by any of these like torque or engine analyzer on the Apple, or the other things. Whether it gets added to the website on JevQ, that keeps getting to be more and more overhead adding those things. See, we're already at the point where JevQ, we can add a feature with a few lines of code. Now adding it where you can see it or changing it on the configuration now is pages and pages. It's kind of an overhead there. But I see a lot of different ways to display the data, and it depends on your car and what you want to do. But ultimately, most people do it through CAN into some sort of smartphone or tablet.
Okay, all right.
One thing, this is using the same processor as the JevQ. In the JevQ code, we already have OBD2 emulation. So we can pick that code up from the BMS here, and you can actually use something like Torque directly to ask for this data. So there doesn't need to be any additional hardware necessarily to be able to do this monitoring. Like you said, you just use a smartphone or a tablet, and it'll come right through an OBD2 port.
Yeah, internally, there's been a lot of discussion about displays. My position is kind of agnostic. There's a lot of work already being done. And then somebody else will want to jump in and actually do a display, well, go girlfriend. But, you know, until they start messing around with the core of JevQ, then I get a little testy about it. But, Colin's got, what we're merging back into with Colin has Helm 327 and OBD2 in it right now. And this will talk to JevQ, but it's the same device. We put the same software in this one. It doesn't even really have to go through JevQ. But it can go into the OBD2 bus. And for $20, you plug in a thing that does Helm. And now you're into a tablet or a phone.
So that
very
actually leads to my question. Given the flexibility of where components can be in the car with CAN bus as an example, this device could be placed anywhere in the car.
You know, I would probably have the hardware board kind of around the battery somewhere, but the other device could be in the back of the dash, could be in the glove box.
Right. And so then that leads into the other question I'm asking is why the need to have the remote shunt? Why not follow Zendyne's paradigm of put the board in the shunt in the same spot and inspect the shunt, let it be there?
Do you see the kind of weatherproof case he's talking about? Well, that doesn't work with battery connections and so forth. The shunt kind of has to be out in your battery system, and we want our electronics to be in a weatherproof enclosure, and they do, or they're kind of inherently a separate thing.
So on the shunt with the temperature sensors, the thought was if you could work all the shunt and have one temperature sensor that help balance out the
sure. It's really, you know, and part of the temperature sensing on the shunt is to be able to eliminate that EMF that's generated by the similar metal contact with the wires to the shunt. Now, if your shunt is made out of copper and you use copper wires, you're probably not going to have much of a thermal difference.
Well, I think we're kind of missing the point of the Zendyne board, guys. You're used to 100 millivolt, 75 millivolt, 50 millivolt shunts. As Ed mentioned, we can use a 10 millivolt shunt with this. Now you understand that current goes through the shunt, and somebody, I think it was Brian, was talking about 45 watts at 800 or 1,000 amps. When we drop that resistance down, that the heating effect goes way down, and that's one of the central issues behind the selection of the Zendyne, because they can do that. So I don't see but one of their central philosophies is to temperature compensate what they do read.
So with the temperature compensation, as you say, the other advantage would be if it was whirlpool, it would be in its own case.
The shunt's not getting very hot. It's just a matter of correcting the reading. We don't need to maintain a temperature on the shunt. In fact, by very low resistance, we're not going to have any temperature gain on the shunt that we really have to fool us very much, other than they compensate their reading
I'm
for
not
whatever
talking
it is.
about cooling the shunt. I'm talking about cooling it. Sorry, I'm not talking about cooling the shunt, just measuring what the ambient temperature of the shunt is so you get an accurate reading, right?
Right.
So if
Maybe I've been mishearing you. I've been hearing cooling the shunt.
oh, well, yeah, okay, no,
What
sorry.
were you saying?
Well, okay, so if we surround the shunt with a water or oil, then we can take that temperature from the shunt as our temperature. You get a better temperature reading. Rather than have
We just need to know what the temperature is. We don't care. And it's not gonna be that hot anyway. But it is gonna vary.
Yeah, the point of the 4 temperature measurements, those are 4 points in the battery pack. Sendyne put thermistors right on their shunt, but again, that was to be able to show the performance of their chip with that evaluation line. For what we're going to do, really, thermistor measurements are at battery terminals in the battery pack.
Yeah, that's a separate topic. I was trying to keep it separate, by the way.
So I guess I was confused as well, that the multiple thermistors on the shunts on the Sendyne board are not exclusively for calibration, but for them to show off and they do a great job.
I'm pretty sure that's.
They are for calibration, but they're kind of showing off, yes. And it's entirely open to question whether we need them at all. And they're kind of working with us on they're
Because
kind of coming
you know,
to.
they soldered wires to their shunt, and they said, you know, that's EMF source, so let's compensate for that, even though it's millimeters away.
But we are definitely going to measure anode temperatures in the battery pack. That's a separate, entirely separate subject, but it is done with the Sendyne board is the problem, yeah. And,
Yeah, I mean, their evaluation line, if you put it on a precision current source, it's flat. No noise, it beats exactly the specs they got.
yeah, this is an order of magnitude different all the way around from like the GLT 505 or 404. I'm convinced that we can screw up the Sendyne pretty badly and still be better than any coolant counter you'll see on an automobile. Anyway. It may be overkill, but overkill is always appropriate. It'll be fun. It'll be an interesting claim.
When you're remoting that shunt, doesn't that remove all your fine traces in the circuitry quite a ways when you have to kick that thing's going to see when you're pushing pretty big currents out of that battery pack? I think it would help with your noise isolation, even though you're optically isolated. Also, they're from the shunt, it's not going to be able to trace too much back to your pot.
These are just for measuring voltage. There's no complicated. This is just looking across the battery pack, the high.
He's saying not having the battery cables with their inductive kick inside our box again.
Yeah.
I would think it would help a lot to have 1,000 amps or whatever, several feet away from your printing circuit board, right on top of it.
Well, so let me clarify that. That particular evaluation module does not do 1,000 amps. That sucker's only limited to 150 volts and 100 amps. Yeah, it's one thing to say, here's the specs, and that's what they would do with remote shunt, but you wouldn't put it right there.
Anybody else? We're at dinner if not. Anything anybody want to discuss?
What's the expected this year, this time next year, or next spring?
Fall 2017, just like
And
about $3,600.
how many DuPonts?
Double the price.
Yeah, it'll probably be a little bit higher than the JevQ, I would think, because of the 2 boards and you know, just kind of an increased component account. But I would certainly like to have it in the store in the $799 range, something like that. It won't be a $2,000 BMS.
And it'll handle up to 400 cells, basically.
And 4,000 cells in one. I guess there is a 106 volt limit
This
right now
particular
on
voltage
4. We could replace the, actually we could replace the resistors in the volts and do a different value. We wouldn't even have to go into the box.
You have a user setup.
Yeah, we could, but we could put our leg resistors that we have on the bolts, change those to a different value and be at a different scale, basically, without ever going in the box.
I mean, you know, more of this would have been done if I wasn't distracted by other things. Conversions, summertime, girlfriend. Job. Right, oh yeah. Job.
When she gets tired of him, he loses his job and it snows, this will move along faster.
Well, no, that's just-